So in this lecture, we continue talking about Bowen's topological entropy. Eventually, we'll show it's the same as the one with open sets, but now we'll just work with it. Certain properties of topological entropy are simpler with Bowen's definition. Now, one disadvantage of Bowen's definition is that at this point, it depends on the metric. So all our definitions had a specific metric in them. And it turns out that at least on compact metric spaces, that metrics that define the same topology give rise to the same entropy. So let me review some basic topology of metric spaces. So the setup is we have a metric, and remember what it means to be an open set. It means that every point in the open set has a ball contained in the open set. So that's what makes an open set open. The complement of an open set is called closed. I didn't write that down. The topology induced by the metric is the collection of its open sets. So sometimes a topology is described abstractly, but let's just be concrete since we have a metric. So the collection of open sets gives rise to the topology, or is the topology. And here's a basic definition about metrics, is the two metrics are equivalent, so that's the operative word here, if they define the same topology. All right, so U is D open if and only if it's D prime open. All right, so they give the same open sets. So here's an easy exercise that two metrics are equivalent if for all x and all epsilon bigger than 0, you can find a, so here the metrics are showing up here. You can find a D ball contained in every D prime ball, and you can find a D prime ball inside every D ball. All right, so here's a picture if you have square balls and round balls. So here you get one inside the other and you need both of them. So here's a standard example from basic topology. You have the Euclidean metric, and this guy is called the taxicab metric, and its open balls look like this. And so in each disk, there's one of these triangle balls, and in each triangle balls, there's contained inside one of these open balls. So these are equivalent metrics. They give rise to the same topology on the plane. All right, now I want to remind you about continuity and express it in terms of balls, because that's what we're going to need. So remember, function is continuous if for all epsilon, and this is continuous at a point. If for all epsilon, there exists some delta, so that if y is within delta of x, then the distance between f of x and f of y is less than epsilon. And the distinction here with the next stage is this epsilon and this epsilon is chosen, but this delta depends on x. Now, uniform continuity says that the same delta works for all x, and so if any pair of points is less than delta, then their image is less than epsilon. So this is uniformly continuous. So an example of a not uniformly continuous function is 1 over x. So this maps 0 infinity to 0 infinity, but when you're down here, nearby points get blown really far apart. So there's no uniform constant. All right, so now we're going to rephrase these definitions in terms of balls. So once again, this is just kind of chasing through the definitions. So continuity is for all epsilon, there exists a delta with the delta ball at x. So that's this condition. But when you take the image you get here, you're inside the epsilon ball at f of x. And the uniform condition is exactly what you think, is the epsilon and delta work the same for all x. I'm sorry, the epsilon is given, and then the delta is the same for all x. All right, so that's uniform continuity. So this is not uniformly continuous. But notice it's defined on 0 infinity. And so it's the non-compactness that allows it to be not uniformly continuous. All right, so the next fact is translation. So D is equivalent to D prime if and only if the identity is continuous. So if you just track through what these conditions say, if F is the identity, and of course the identity inverse is continuous as well, then you get this. So probably should say bicontinuous here, just to make it clearer. All right, so let's say bicontinuous here. Now here's a theorem from topology so here's a theorem from topology, says that if you have a continuous function and a compact domain, then it's uniformly continuous. All right, so if we put the pieces together, if we have a compact space and equivalent metrics, then the identity is uniformly continuous. And I guess I should be saying here as a uniformly continuous inverse, right? It's definitely a bijection. That, let me not speculate here. So this happens, so the point of this is that if we're in a compact space and we have equivalent metrics, then our deltas don't depend on the point. That for all x, you can, given the epsilon, you can find the same delta so that the d ball is contained in the epsilon d prime ball, and the delta prime ball of d prime is contained in the epsilon ball of d. All right, so you get uniform deltas here, and that's what's going to be important in showing the entropy is independent of the metric. All right, so now let's get back remembering our definition of the entropy. We have these new metrics dn, and it's easy to check. This again, maybe on homework, but it's easy to check if the two metrics are equivalent. If you have these conditions, if the two metrics are equivalent, then all the dn's are equivalent with the same constants. All right, now in the theorem, it's useful to notice, you'll notice for given an epsilon, there exists a delta. So delta depends on epsilon. So it's useful to have that explicit, and we write delta of epsilon and delta prime of epsilon to denote the dependence on epsilon. And notice that as epsilon goes to 0, these guys go to 0 also, right? Because this guy has to be contained in this guy. This guy is contained in this guy. And there's a compactness in there as well. Okay, so here's the theorem we've been shooting for. If you have compactness and equivalent metrics, then h of f computing Bowen's definition gives the same result no matter which metric you choose. All right, so let's use, remember we had various definitions. Let's use separated sets. All right, so if we have a dn minus n epsilon separated set, okay, so the distance apart here is epsilon under dn. Then because we have the same constants, then and we have a ball inside here, so it's also dn, but now the ball inside is delta of epsilon. All right, now this is true over every k. All right, so that tells us that when we take the max, as we need to do when we use the separated sets, we take the max, we get the max of the cardinalities of the separated sets is bigger than the k prime one. So k prime is the same thing committed with the prime, right? Because every k that's an epsilon separated with respect to dn is dn prime separated with respect to delta epsilon. All right, that's just because this ball's inside that ball. All right, so now we remember what you do. You take this guy, and then take the log and divide by n, pass to the limit, take the limit as epsilon goes to 0. And so first, we don't let epsilon go to 0. We just take that limit, 1 over n. And then we let epsilon go to 0, so delta of epsilon goes to 0. And we get h of f is less than or equal to h prime of f. So this is just from using, and here we use just this uniform equivalence of the two metrics. All right, and then there was nothing special about doing it in this order. We do it in the other order. All right, so this gives us independence of the entropy from the choice of metrics, as long as the metrics are equivalent, as long as they define the same topology. All right, so the next thing is to show that the entropy as defined by Bowen is a conjugacy invariant. So we showed this is true for the open set definition already, and we're eventually going to show that the open set and the Bowen definition are the same, but this is pretty easy to prove directly, and it illustrates a lot of the machinery we've developed so far. So what's the setup? We have a map F of X. We have a map Y of Y. They're both compact metric spaces. We have phi. We have our metrics D and D prime. Phi is a homeomorphism. Then the entropy upstairs is the same as the entropy downstairs. And again, this is all with Bowen's definition. All right, so let's start with a simple assumption, which isn't always true, but let's assume phi is an isometry. All right, so what does it mean to be the isometry? That means it preserves distance. So we've seen before self-isometries, but now this is an isometry from one metric space to a different metric space. So it preserves distances. So in particular, it takes n epsilon separated sets to n epsilon separated sets for G on Y. All right, and then you just run through the whole machinery. So H of F has the same entropy, F has the same entropy as G when phi is an isometry. All right, so how are we going to put that to use? Well, we define a new metric. Well, we have to prove it's a metric. We prove it's a metric, and then we define it by d double prime of y1 is we take d of phi inverse of y, phi inverse of y2. All right, so this is just like pushing a measure forward, but now we're pushing a distance function forward. All right, so the claims are that this is a metric, and then with respect to this metric, phi is an isometry from xd to y d double prime, where that's the new metric here. And finally, the d prime and d double prime are equivalent metrics on y. That'll follow from phi being phi being a homeomorphism. All right, so let's look at if we can prove it given these three facts. All right, so if we know that this is an isometry, then the special case tells me that the entropy of F is the same as the entropy of G, now computed with d double prime. But on the other hand, the theorem we just proved says that these are equivalent metrics, and so this guy equals this guy. The metric computed with the d prime metric is the same as the metric with the d double prime metric, so this equals this equals this, and we're done. So we have to prove the claim to finish up. All right, so to show it's a metric is pretty easy. I won't do that. And let's see it's an isometry. So let's compute d double prime of phi of x1, phi of x2. By definition, that's d of phi inverse of phi of x1, phi inverse phi of x2, but phi inverse phi is the identity. So it's the distance, the x1, x2. All right, so now for the equivalence of the the equivalence of the metrics, we have to show d prime and d double prime are equivalent. So I'm just going to keep restating that until it's hopefully obvious. All right, so what do we need to prove? We need to prove that for all epsilon there exists a delta so that a delta dw prime ball is inside a d prime epsilon d prime ball, and also the other way around, that there's a delta prime ball under d prime is contained in the epsilon ball under d double prime. All right, what does it mean for this ball to be inside here? It means that if you're less than delta distance away from y with respect to this metric, then you're less than epsilon distance to y with respect to this metric. All right, so this inclusion of balls, which is the inclusion needed for equivalent metrics, is the same as this pair of implications with inequalities. All right, I won't repeat this one, it's just the obvious. All right, so now let's take the definition of d double prime and remember what it was. It's d of phi inverse y1. So we have to show, given epsilon, there exists a delta, so that the distance between phi inverse y1 and phi inverse y2 is less than delta, and implies that d prime is less than epsilon. And we need to go to the other way around with d prime implying d double prime. So let's first look at this one here. This should look familiar. This is exactly the statement that phi inverse is continuous. Right? Given an epsilon, there exists a delta, so that we're less than delta prime in this case less than epsilon. Now for this guy, it looks backwards, but we just do the usual trick of x1 equals phi inverse y1, x2 equals phi inverse of y2, then this becomes the continuity of phi. So the equivalence of the two metrics is really just the continuity of phi. It's a little bit disguised, but that's that. So before I prove some more basic results about the entropy, I wanted to talk about an important class of examples, and that's in the shift space. So we've seen already that in some sense entropy is a way of, you can think about it as taking a partition, dividing the space into outcomes of an experiment, turning that into a stream of bits or data or numbers or whatever. And you can think of them as in a shift space. So here's some terminology. If you have a subset that's compact and shift invariant, it's called a subshift. So this is a little confusing since the shift is the map, but this is the accepted terminology. So the language of the subshift is the set of all words. These are finite words that occur in any sequence. All right, so you have all these infinite sequences and they have finite chunks, which are words. You collect them all together and that's called the language. All right, obvious terminology. So we want to measure the complexity of the language of X. So for that, let's look at the number of different words of length n. All right, so you pick, there's some number like 23, and you look at all the words of length 23, and you count how many different ones there are. All right, so this is measuring the complexity. So we're going to measure the exponential complexity, because that's the thing that's associated with the entropy. So what's the exponential complexity? Is we take the log of the number of words of length n divided by n, take a limit, familiar limit, and that's called the exponential complexity. So recall what that means. It means that if the exponential complexity is some number eta, then the number of words of length n is growing like eta to the n. If this is 2, for example, it's 2 in the 2 shift, then this guy is growing, well, yeah, so now, a little confusing here, this isn't quite right. So if the exponential complexity is growing like log eta, then that means that the word growth is like eta to the n. All right, there's this log here that I forgot about. We're computing the growth rate of not the nth root, but the log. So you end up with a log, and then you get this guy. All right, so here's the fact, and the proof is just like proofs we've seen with limits like this before. The exponential complexity exists, and in fact, it's the infimum of the log of Wn over n. All right, so the proof of this is, not surprisingly, we use subadditivity. First, you observe that any allowable word of length m plus k must consist, so it's length m plus k, and it has two pieces. One of length m, we arbitrarily chop it up, one of length m, one of length k. So there's some choice here, there's some choice here. So that implies, and then of course the number of choices is the product, that the number of words of length m plus k is less than equal to, isn't necessarily every word here. It can be concatenated with every word here, but this is certainly an upper bound. All right, so we take the log, we get the subadditivity, and then we use the subadditivity theorem, and we get this limit exists and equals this. All right, now the theorem, which we'll eventually prove next time, we're going to develop some machinery here, is that if we have a subshift, then the topological entropy is equal to the exponential complexity. All right, and so I think this is enough for one lecture. So I'm going to stop here, and next time we'll give the proof of this theorem, which will need some more information about shift spaces.